Hello everyone, welcome to lecture 4. In the last lecture, we studied free and force vibrations of single degree of freedom undamped systems. In practice, however, systems dissipate energy when they vibrate, and this dissipation affects the free and force response of the system. So, in this lecture today, we are going to study the free and force vibrations of single degree of freedom systems with viscous damping. So, today's topic is free and forced vibration of single degree of freedom systems with viscous damping. Right. So, that is nothing but the topic we are going to study today. What is damping? So, systems have some mechanisms through which they dissipate energy of the system, and damping refers to all such mechanisms which exist in the system, right. So, damping refers to dissipation of energy in the system, dissipation of energy of the system, right. That is nothing but damping, and such dissipation may occur because of several reasons. For example, there may be viscous friction, right, which may occur if there are the system while vibrating is subjected to forces due to fluids, gases and so on, right. So, they generate viscous forces which tend to resist the motion of the system, and in the process they dissipate energy of the system. Then there could be dry friction, right, which is referred as Coulomb damping. So, again if there is dry friction, that is then again the friction forces they do work against the motion of the body, right, and in the process they dissipate energy. Viscous friction of course can be referred as or is referred as viscous damping. Then there may be dissipation of energy due to hysteresis effect. Often referred as structural damping. Okay, so that I think we will study more later. Then there could be some other internal mechanisms, some other mechanisms internal to the internal to the body, which again may cause dissipation. There is also something called acoustic damping. Because when a body or system vibrates, it also radiates sound, right, and therefore the energy of the system is also partially dissipated away through the propagation of sound. So, that is referred to acoustic damping. So, these are the sources through which the energy of the system may be dissipated, and all of them are referred as sources of damping. But in practice, we often use a viscous damping model. We often use a viscous damping model in the form of a viscous dashpot to represent energy dissipation in the system. So, irrespective of the actual mechanisms that are present and which are responsible for dissipation of energy, we may use a viscous damping model to represent the damping in the system, right. And this is because the viscous damping model offers ease in the mathematical analysis of the system. Okay. So, this offers ease in the mathematical analysis. Okay. So, viscous dashpot is represented by a piston like this, a piston which is moving in a cylinder filled with oil. Okay. So, this is nothing but viscous dashpot, and so if we plot the force of resistance of this then it is proportional to the velocity, the relative velocity between the two ends of the damper, right. So, this is nothing but the force of resistance of the viscous dashpot, and F is proportional to velocity, and the constant of proportionality is C, which is referred as viscous damping coefficient. Damping coefficient, and it has units Newton per meter per second, right. So, the force of resistance, right, per unit velocity, relative velocity between its ends. So, therefore, first now we are going to study the free vibration. Okay. So, we are going to study the free vibration of a single degree of freedom system with viscous damping, and therefore, let us sketch the system. Maybe we can show it like this. Okay. So, that is mass, stiffness and damping. I would like to emphasize that this is a single degree of freedom system, but actually it is a single degree of freedom model of a practical system, right. So, any practical system we have modeled it through a single degree of freedom model, and this system we are referring as single degree of freedom system with viscous damping. So, now we would like to write equations of motion and then analyze the free vibration characteristics of the system. So, let us say this is the the static equilibrium position, right. Let us say this is the static equilibrium position, with respect to which we are going to measure the vibration of the system, right. So, let us say the system is displaced by a displacement x like this. Okay. So, that is nothing but the displacement of the system, and then we would like to draw the free body diagram in this condition of the mass, right. So, the Kx is going to be the force due to spring, and we will have Cx dot as the force due to damper, and this mass has an acceleration of x double dot at this position. Okay. So, now we are in a position to apply the relevant physical law here in order to write the equation of motion. So, if we apply Newton's law, which says that the mass into acceleration is equal to summation of algebraic summation of all the forces which are acting on the system, right. So, since the force due to spring and force due to damper, they act opposite to the acceleration, we take them as negative. So, mx double dot is equal to minus kx plus minus cx dot, right, and then we have mx double dot plus cx dot plus kx is equal to 0. So, that is nothing but the equation of motion, right. See, nothing but the equation of motion. Okay. So, now we would like to solve this differential equation. It is a second order differential equation, a linear equation of second order. We would like to solve this equation. So, we note that here we have an additional force term Cx dot, which is proportional to velocity, and because of that this equation does not represent simple harmonic motion. Okay, it does not represent simple harmonic motion, because in the simple harmonic motion the acceleration has to be proportional to only displacement, right. So, therefore, the solutions we assume in the undamped case, right, like A cos omega t or B sin omega t, those solutions no longer will be the solutions of this differential equation. So, physically speaking, under the free vibration, what is going to happen is that the displacement of the mass would gradually decay with time, because the energy of the system would be dissipated by the damping forces. And therefore, we require a mathematical solution which can capture this decaying nature of the displacement, and hence we assume a solution which has the ability to model decay of vibration. So, let us assume x of t as say a e to the power s t. Okay. Here s is a complex number. Okay, it is a complex quantity. Okay. So, if this has to be the solution of the differential equation, it must satisfy the differential equation, and hence we substitute this into the differential equation. When we do that and we do the necessary algebraic we do the differentiation, then what do you get? We get s square e to the power s t a s e to the power s t plus k a e to the power s t is equal to 0, which means ms square plus c s plus k e to the power s t, right, also a is equal to 0, correct. So, now here a into e to the power s t cannot be 0, right, because if that is 0, then the displacement of the mass is also 0, because that is the solution we have assumed, and that would not reflect the vibratory nature or vibratory motion of the system, and hence it cannot be a valid solution. It is not a solution of the system, and hence the other way this equation can satisfy is when ms square plus cs plus k is equal to 0. So, if that is 0, then also the solution a into e to the power s t would satisfy the differential equation. Let us write that again. So, the equation we have ms square plus cs plus k is equal to 0. So, S12 would be minus c plus minus under root of square minus 4 a k m upon to m, right. So, that is going to be the relationship. So, this is I think the correct formula, right. So, therefore, the general solution is given by a linear combination of two solutions. So, one solution is a1 e to the power s1t, and other solution is a2 e to the power s2t. So, a linear combination of these two solutions gives us the general solution. So, the nature of X solution depends on nature of S1 and S2, right. So, the nature of X depends on nature of S1 and S2, right, and the nature of S1 S2 depends on the sign of the this term in the square root c square minus 4m, phi square minus 4km, and depending upon whether c square is more than 4km or less than 4km would determine the nature of the root, and hence the boundary between the transition from say a positive value of c square minus 4km to a negative value of c square minus 4m, that transition is decided by the value which makes c square equal to 4km, right. So, therefore, if we say c square is equal to 4km, right. So, so what is the damping coefficient which makes this equation satisfy, right, that is c square is equal to 4km. Let us determine that damping. So, that would be nothing but 2 under root km, okay. So, when the damping in the system, the viscous damping coefficient of the system, it is equal to 2 under root km, then this c square minus 4km would be equal to 0, right, and such a damping and that would make the two roots S1 S2 equal, okay. So, such a damping coefficient in the system is referred as critical value of the damping in the system, right, and hence we say that Cc is equal to 2 under root km, where Cc represents critical damping coefficient. So, this is nothing but the critical damping coefficient, and then we define a non-dimensional factor to quantify damping. We define a non-dimensional factor to quantify damping in the system, right. And that we define as the ratio of the actual damping coefficient and the critical value of the damping coefficient. So, we that refer as damping factor C upon Cc. This is referred as, this is called as damping factor or viscous damping factor, okay, and is the ratio of the actual damping coefficient which exists in the system to the critical value of the damping coefficient. Right. So, let us now rewrite these roots in the form of damping factor and natural frequency of the system. So, we have S12 is equal to minus C plus minus under root of C square minus 4 km divided by 2m, and this we can write as minus C upon 2m plus minus, right. If we take 2m inside the square root, we get C by 2m square minus 4 km upon 4m square, right. So, that makes it k by m. So, if we look one by one at these factors, then C by 2m can be written as Cc times damping factor, right, and Cc can be written as 2 under root km, okay, and that becomes zeta under root k by m, right, and under root k by m is nothing but the natural frequency of the system. So, this gives zeta omega n. So, c by 2m is nothing but zeta omega n, and k by m is nothing but omega n square, and hence we get S12 as minus zeta omega n plus minus zeta square omega n square minus omega n square. So, k by m is nothing but omega n square, and therefore, we can write this as minus zeta plus minus under root of zeta square minus 1 times omega n, right. So, we see that the two roots of the complex roots of the system, they depend on the damping factor and the natural frequency. And now, depending upon whether the damping factor zeta is more than 1, less than 1 or equal to 1, the nature of the roots would be determined. So, therefore, we have these three cases, and let us study these cases one by one. So, we first of all take the case of zeta more than 1, right, and this is referred as overdamped system. Because the damping in the system is more than the critical value of the damping. Now, in this case the roots would be S1 and S2, these roots would be real and unequal, right. Roots would be real and unequal because zeta square minus 1 is positive. So, the general solution will be given by x of t. If I take zeta omega n t common, then it is minus zeta omega n t a1 e to the power plus under root of zeta square minus 1 omega n t plus a2 e to the power minus zeta square minus 1 omega n t. So, this is the general solution, and then the a1 and a2 are arbitrary constants. A1 and A2 are arbitrary constants, and they depend upon the initial conditions. They depend on the initial conditions on the displacement and velocity of the mass of the system. So, if we plot say the response of the system, then it is going to look something like this. The response of the system, let us say if we take initial conditions as at t is equal to 0, x of t is equal to x naught, right, and the velocity x dot t is equal to v naught, right. So, if you take let us say a certain value of x naught, so let us plot x here and t here. So, the x of t, let us say if the velocity v naught is 0, then this is going to decay like this. And if let us say, so this for this you can see velocity is 0 and the displacement starts from x naught. If v naught is positive, then this profile may look like this, something like this. And if velocity, so this is velocity more than 0, and if the velocity is negative, then it may take this kind of shape. Okay, so this is v naught less than 0. So, you can see the system basically the displacement decays with time, and depending upon the combination of initial displacement velocity, different shapes of these curves are possible. But one characteristic is common, that the displacement decays exponentially with time, and it does not oscillate, there are no oscillations in the system, right. So, we have decay of or exponential decay of the vibration, right. The displacement of vibration decays exponentially with time, and there are no oscillations. So, in fact, it is it's it's not exactly vibration, because it's just displacement is just decaying with time. It does not cross the repeatedly the mean position, right. At most it may cross once the mean position, depending upon if the velocity is negative, right, it crosses, but otherwise it does not cross repeatedly the mean position, and hence that way it's not, there are no oscillations. So, that is the overdamped system, right. If zeta is equal to 1, right, then this is called a critically damped system. And in this case, the roots S1 and S2 are real and equal. The roots are real and equal, and and they are simply equal to S1 is equal to S2 is equal to minus zeta omega n, that is all. And therefore, the general solution is given by x of t is equal to a1 plus a2 t e to the power minus zeta omega n t. So, in this case we note that not only a1 e to the power minus zeta omega n t satisfies the differential equation, but a2 into t e to the power minus zeta omega n t also satisfies the differential equation, and that makes the general solution, right. So, simply adding a1 e to the power minus zeta omega n t and a2 e to the power minus zeta omega n t would not make up a general solution, because then we can combine both the terms and then we end up with only one arbitrary constant in the solution, and that would not represent a general solution, simply because the system or the differential equation is of second order, and then there should be two independent arbitrary constants in the solution in order for the solution to represent the general solution. So, this is the general solution, but again in this case we note that because of the presence of this term, right, e to the power minus zeta omega n t, the displacement is going to decay exponentially with time. As time t increases, because of this factor e to the power minus zeta omega n t, the displacement will reduce exponentially with time. Okay. So, if you plot again the displacement is a function of time, it is going to look something like this. So, theoretically it takes infinite time for the displacement to reach mean position 0, right. But in practice, in addition to the viscous damping which might be there may be other damping mechanisms which might be present, because of them, because of which the system would come to the rest or the mean position in a finite time. So, here also again we observe that there are no oscillations, right, and the response decays exponentially. With time. Let us now look at the third case where zeta is less than 1, and this case is called as a case of underdamped system. This is nothing but underdamped system. So, in this case what is going to happen if we look at the roots S1, S2, then the roots are minus zeta plus minus under root of zeta square minus 1 omega n, right. So, in this case, because zeta is less than 1, zeta square minus 1 is negative, which makes this square root zeta square minus 1 as a complex quantity, and therefore, we can write this as minus zeta plus minus I under root of 1 minus zeta square omega n. That is how we can write down. So, now therefore, the roots are complex conjugate, right, because S2 can be written as complex conjugate of S1. So, if S1 is minus zeta plus I under root of 1 minus zeta square omega n, then S2 is simply minus zeta minus I under root of 1 minus zeta square omega n, right. So, only the sign of the imaginary part is different in the two roots, the sign of real part is same, and hence they are complex conjugate. So, in this case, if we now write the general solution, then the general solution is given by A1 e to the power S1t, right. So, we can then write minus zeta plus I under root of 1 minus zeta square omega n plus A2 e to the power minus zeta minus I under root of 1 minus zeta square omega n. Of course, I am missing t here, t. Okay. So, that is nothing but the general solution, and I can take e to the power minus zeta omega n t common, and then I am left with A1 e to the power I under root of 1 minus zeta square omega n t plus A2 e to the power minus I under root of 1 minus zeta square omega n t. Okay. So, now I can use Euler's identity, and then which says that e to the power I theta is equal to cos theta plus or maybe I can write here plus minus, right, e to the power I plus minus I theta is equal to cos theta plus minus I sin theta, correct. So, if I use that Euler's identity, then I can simplify this equation, and then let us write the simplified equation. So, using the Euler's identity, what I am going to get, I would have a cos term. Let me write down first cos term, cos under root of 1 minus zeta square omega n t, right. So, then I have here A1, so I would have A1 plus A2, right. That is what I would get from the term from the other from the e to the power minus I theta, and then I have plus A1 plus A1 minus A2, right. I sin under root of 1 minus zeta square omega n t, right, and then also I have the factor e to the power minus zeta omega n t, right. Let us check it is correct or not. So, e to the power I theta was cos theta plus I sin theta. So, I think it looks right. So, now so this is what we are getting, right, and if the vibration x of t is real, right. So, if the system is vibrating, the displacement of the system has to be real quantity, and for that thing to happen, the A1 and A2, right, they have to be complex conjugate. Then constants, arbitrary constants A1 and A2 have to be complex conjugate. because then only the right hand side of this equation would yield a real quantity, right. So, A1 and A2 would be complex conjugate of each other. So, when they are complex conjugate, A1 plus A2 would be a real number, right, because the imaginary parts would cancel out, and then let us represent that as some constant d, right. And similarly, the A1 minus A2 into I would again be a real number, because A1 minus A2 would lead to a imaginary number, and that multiplied by I would be a real number. So, let us represent that by another constant E. If we do that, then the general solution can be written as x of t d cos under root of 1 minus zeta square omega n t, right, plus E times sine under root of 1 minus zeta square omega n t, right, multiplied by e to the power minus zeta omega n t. Okay. And then using trigonometry, we can also now combine these cos and sine terms, right. They have the same, I mean the argument, right. So, we can combine these two quantities using trigonometry, and we can then rewrite this equation in this form: a cos zeta omega n square t minus phi, right, and into so let me add e to the power minus zeta omega n t in the beginning. So, we will have so that is nothing but the solution we get, general solution. So, here a and phi, they are arbitrary constants, and they depend on initial conditions. So, we can find them if we are given the initial conditions. Okay. So, we need two initial conditions here, and from them then we can apply those conditions to this equation, and then we will get two equations from which whose solution would lead to a and phi. Let us try to now interpret what this solution represents. This represents that the amplitude, so if you look at this part, this is the amplitude of the vibration, right, amplitude of displacement, and this is basically a function which decays exponentially, whose value reduces exponentially with time, because in the exponent we have the minus zeta omega n t, and for a time t is positive, so hence and zeta and omega n are positive for the system, and hence the exponential this term is going to decay with time. So, we are going to have an exponential decay. So, we have exponential decay of amplitude. The second thing is that if we look at this one, this quantity is a cosine term, right. So, it represents oscillations, because cos and sine term, they are oscillatory and they represent oscillations, and the frequency of the oscillation is given by the coefficient of time t. So, whatever is the coefficient of time t, that represents the frequency of the oscillation in radians per second, right. So, therefore, we see that there are oscillations, right, vibration is there, and then the frequency of oscillation is nothing but the coefficient of t, in which in this case is under root 1 minus zeta square omega n, right. And because the system is oscillating under damped state, the system is damped, we also often called it as omega d, that is the frequency of damped oscillations, and hence we represent it as omega d. Okay. So, the damped frequency of oscillation, it depends on the natural frequency of the system omega n and the damping factor zeta of the system, and of course, it has the units radians per second. The third thing we see is that we have this phi here, right. This phi represents phase lag. So, this phi, it represents phase lag, which means that the system response, right, it reaches to the maximum value with some time lag with respect to the origin. When the vibration was started, the system maximum response has a time lag. It does not reach to the maximum at the same instant, it reaches little bit late, and that is being quantified by this phase angle phi, and of course, its units are radians, right. So, this is nothing but how this solution can be interpreted. Let us try to sketch this. So, if you show the displacement on the y axis and time on the x axis, then this is going to look something like this. Something like this, right, and this is for a certain value of zeta, right. So, if you increase the value of zeta, then the curve would change in this manner. If you increase the value of zeta, then it may be something like this. So, this is the damped free vibration response for a higher zeta, and this is for a lower zeta. I am sorry, I have written the opposite. Now, this is lower zeta, and this is higher zeta. Okay. So, if you increase the damping, the rate at which the displacement reduces or decays, that increases. So, there is a faster decay of amplitude when the zeta increases, right, for an underdamped system. So, of course, if there is no damping, then the oscillations are going to continue forever, right, like this. They would not decay, and the amplitude of the oscillation would stay constant, like this. There is no decay, you can see there is no decay here, but in this case you can see there is decay, the amplitude is decaying with time, and that this is an exponential decay. This envelope of amplitudes is an exponential curve. Here also, that is an exponential decay. Now, the another question we can ask here is how the rate of decay is dependent on damping, right. So, the energy of the system, how it is dissipated, and how it is related with the damping in the system. So, for that purpose, let us try to look at decay of energy, decay of system energy. The energy of the system, it consists of two parts, the kinetic energy and potential energy, right, and therefore, at any instant of time we can find kinetic energy of this single degree of freedom system as half mx dot square plus half potential energy is half kx square, right. So, it means if I am given x of t and x dot of t, I can then determine E of t, right. So, if x of t and x dot of t are given, then we can determine how the energy of the system varies with time, right. And now if you make a plot of this as a function of time, then we would understand that how the system energy is decaying with time. So, let us try to sketch these plots, when we have, let us say, say first overdamped systems, right. So, if you take overdamped systems, then if you plot the E is a function of time. By the way, why E is supposed to change with time? Why it is going to decrease with time? Simply because there is damping in the system. The system would decay, would dissipate this energy, as the vibration proceeds, right, as it progresses, right. So, in every dt time, the system, some of the energy would be lost in doing work against damping forces, right, and therefore, system energy is going to decay with time. So, let us talk of underdamped system. So, if we take a system which is underdamped, then and if we assume the damping factor, let us assume that the mass and stiffness are same for all these systems, and if the damping factor is very high, and the limit could be say infinitely large value of damping factor. So, in that case the system energy would not decay with time, because the infinite damping force would not allow system to displace or deform, and hence there would be no loss of energy, right. Though damping force is high, but there is no deformation or velocity, and hence there is no loss of energy, and hence what is going to happen? We will simply have the energy of the system staying constant. So, this is when damping factor is theoretically infinite. Now, when damping factor is reduced, then the rate of the energy would start decaying, right. So, if you increase the damping factor, then system energy would start decaying in this manner as with time, and then if you reduce the damping factor further, again the rate of decay would increase, increase like this, and then it would reach to a maximum decay value, right. This is when the damping factor is equal to 1, right. When the system is critically damped, the rate of decay of energy would be maximum for an overdamped system, right. So, this is nothing but the zeta reducing, zeta is reducing in this direction, right. Now, let us talk of underdamped systems. Now, for the underdamped systems, we can have the smallest damping possible as no damping, right, when damping is 0. So, in that case again the system energy is not going to decay with time, the total energy of the system would stay constant, and hence we will have energy of the system staying constant with time. So, such a system would keep on vibrating and the total energy of the system would stay constant. Only the kinetic and potential energies instantaneously will be changing and changing hands basically, right. Kinetic energy converting to potential energy and potential energy converting back to kinetic energy, but the total energy would stay constant. But now if we have some damping, right, then what is going to happen is that the system energy would then start decaying, total energy will start reducing with time, and then the graph may look something like this. Okay. So, that is when now there is some zeta, and if you increase the damping further, but keeping the system underdamped, then the rate of energy decay would increase more, right, it would further increase like this, and then when it becomes almost close to 1, right, little bit less than 1, because if it becomes equal to 1, system no longer would be underdamped, right. So, if you keep it almost close to 1, then it would basically reach to the rate of decay closer equal to that of a critically damped system. So, this would be the basically damping level in the system. So, this is when zeta is almost equal to 1 or but little bit less than 1, so that it remains underdamped. So, what we see is that, so here if I show the damping level, so this is zeta is equal to 0, right, and this is zeta is equal to 1. So, you can see here damping is basically increasing. So, from this I think discussion some important points emerge. One thing is that we can't say that if damping is increased, then the decay of system energy or displacement is always going to increase, right? It is going to, the rate of decay is going to increase, right? There is no monotonous change, because we see that for overdamped systems the rate of decay increases when the zeta is reduced, but for underdamped systems rate of decay increases if zeta is increased, right? So, these are two opposite effects. So, the point is that the power dissipated from the system, or the rate of dissipation of energy, which is nothing but the power dissipated, it depends on the damping force and the velocity. So, having higher damping factor will increase the damping force, but the other quantity which affects power dissipation is velocity, and that also is affected because of damping factor, and therefore both need to be seen to determine the power dissipation, right. So, therefore system with with damping factor equal to the critical value, that will have the highest rate of decay of energy, right. So, the rate of decay of energy is highest when the system damping is equal to critical damping, right. So, the rate of decay is highest when system is critically damped. Okay. So this is the other important thing we need to look at is how is there a relationship between the ratio of amplitudes, right, in different cycles with the damping factor, and that relationship is captured by what is called as logarithmic decrement. So now we talk about what is called as logarithmic decrement. Logarithmic decrement basically gives the relationship between the ratio of amplitudes of different cycles of vibration with the damping factor, right. So, we know that the equation for free vibration of an underdamped system is given by a to the power minus zeta omega n t cos omega n under root of 1 minus zeta square t minus phi. And if we sketch the free vibration profile, then it may look something like this. And so on. So, if let us say the amplitude here at instant t1, which represents the time when the amplitude is reached, that is x1, and say after n number of cycles, right, if the amplitude is xn, then we would like to determine. So, at instant t1 we reach an amplitude xn after a lapse of n number of cycles, then what is the ratio of x1 and xn? That is what we would like to determine. So, therefore, we would like to write x1, and we will like to find x1 as x at t1, and that would be nothing but a e to the power minus zeta omega n t1 cos omega n under root of 1 minus zeta square t1 minus phi, right. Similarly, we can write down xn sorry, xtn is equal to a e to the power minus zeta omega n Tn cos omega n under root of 1 minus zeta square Tn minus 1, right. So, now we note that Tn is nothing but T1 plus n times t, because n cycles are elapsed, right. So, therefore, the time Tn would be T1 plus n times the time period. So, this is nothing but the time period T, right, time period of damped oscillations. So, if we now and another thing we note that the cost function is a periodic function, right. So, it means cos omega n under root of 1 minus zeta square T1 minus phi, it will repeat periodically, and hence cos, it will be equal to cos omega n under root of 1 minus zeta square T n minus phi. So, these two are basically equal, right, and therefore, if we take the ratio now x1 upon xn, what we get is a e to the power minus zeta omega n T1 upon a e to the power minus zeta omega n Tn, and if you substitute Tn here, what we get is e to the power, so a of course cancels out, and then we get e to the power zeta omega n, right, into n t, that is what we get, right. And we also note that the t, which is the time period, it is equal to 2 pi upon omega d, right, which is the damped natural frequency, and damped natural frequency is nothing but omega n under root of 1 minus zeta square. So, this is nothing but t. So, in the light of this, we can then write x1 by xn is equal to e to the power zeta zeta omega n into 2 pi upon omega n under root of 1 minus zeta square. So, omega n cancels out, and then we are left with x1 upon xn is equal to e to the power zeta, maybe let me rewrite again, e to the power 2 pi, right, zeta n upon under root of 1 minus zeta square, that is what we get, okay. And if you go to next page, now if you take log of the two sides, then we get log of x1 upon xn is equal to log of e to the power 2 pi zeta n, right, upon under root of 1 minus zeta square, which leads to 2 pi zeta upon under root of 1 minus zeta square is equal to 1 by n log of e x1 by xn. So, I think this is the final expression we are getting, right, which basically relates the amplitude at the beginning of at some amplitude at some cycle at the beginning of a cycle, and then amplitude after elapse of n cycles, right. So, that ratio, that is x1 by x1, and then n is the number of cycles which are elapsed. So, and this therefore quantity is dependent on only zeta, right, and this quantity then we refer as logarithmic decrement. So, we define this as 1 by n log of e x1 by xn. So, this is nothing but logarithmic decrement. And this quantity, you can see, it depends only on zeta. So, this particular relationship has a great practical value, because we can use this to determine damping in the system. So, if we have a system, let us say single degree of freedom system, and if we know the displacement versus time history under free vibration of that system, if we know the displacement versus time history like this, which can be obtained let us say by measurement, then we can use this relationship to find damping factor in the system. So, we can measure say x1, and then we can measure this x2, right. So, in the present case what is going to happen, x1 by x2, because here n is just 1, right, because only one cycle has elapsed, then in that case this would be simply log of E x1 x2 would be simply equal to 2 pi zeta upon under root of 1 minus zeta square. And then because x1 x2 can be obtained from the measurement, we can find zeta from here, right, we can find zeta in the system. So, damping in the system can be estimated in this manner. Let us now consider the force vibration of the single degree of freedom system with viscous damping, and we are basically going to consider the harmonic forces, right. So, force vibration right, and the equation of motion with force vibration can be written as mx double dot plus cx dot plus kx is equal to f of t, right, and here f of t is a harmonic force. So, f of t, let us say it is a cosine force f naught cos omega t, where omega is the excitation frequency. Now, the response of the system would consist of two parts, right, complementary part and particular part. So, the x of t will be equal to xct plus xpt, the complementary part and particular part. So, let us first of all find the particular part or particular solution. Let us determine this first. And now we are going to use here the complex exponential method we studied earlier in the force vibration analysis of undamped system. Okay. So, in the complex exponential method we basically find the response of the system to complex exponential force. Okay. And then once the response has been found, we then take the real part of the response. Okay. So, that is the method we studied earlier. So, let us take the complex exponential force as f of t is equal to f naught e to the power I omega t, and we can see that the real part of f bar t is basically the actual force f of t. Now, let the particular part of the solution to this complex exponential force is given by x p bar t, right, is equal to x p o bar e to the power I omega t. So, we are assuming the response to be of the same form, it is at the same frequency omega, and its amplitude is x p o bar. Okay. So, this x p o bar in general could be complex, and x p bar is the particular part of the response. So, the over bar has been used to indicate the complex exponential nature of that quantity. So, if you substitute this in the equation of motion, what do you get? Minus m omega square x p o bar plus I omega, right, c x p o bar plus k x p o bar, okay, and then e to the power I omega t would cancel out from the right and left hand side. So, this is what we get, and therefore, if you simplify, what we get is x p o bar is equal to f naught upon k minus m omega square plus I omega c, right. So, this is the expression we get for the amplitude of the complex exponential response, right. Now, this can be expressed in the magnitude and phase form like this. We can also write this as the magnitude of this is f naught upon square root of k minus m omega square plus omega c whole square into e to the power minus I psi, correct. So, here we have separated the magnitude and the phase part, okay, and what is psi here? This 10 psi, or maybe we can directly write psi. So, what is psi here? psi is equal to basically tan inverse omega c upon k minus m omega square, and psi is basically the phase lag. This is actually the phase lag, which shows the angle by which the particular part of the response lags the applied force. We can also further divide this, the numerator and denominator, by k, and make use of the properties that omega n is equal to under root k by m and zeta is equal to c upon cc, right. So, if you make use of omega n and zeta here, so we can write this expression for xpo bar also in this form. So, we can write this as x static upon under root of 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square, okay, multiplied by e to the power minus I psi, right, and the phase lag psi can also be written in terms of omega n and zeta as 2 zeta omega upon omega n divided by 1 minus omega upon omega n whole square, okay. So, in this way we obtain basically the magnitude and phase of the amplitude of the particular part of the response. Therefore, the complex response is given by x p bar t is equal to x p o bar e to the power I omega t, isn't it? And then we can find the actual response x p t as real part of x p bar t, isn't it? So, if you substitute now expression for x p o bar here, we basically obtained a real part of the response as x static upon under root of 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square, okay, and then e to the power I omega t into e to the power minus I psi will become e to the power I omega t minus psi, and then the real part of that would be cos omega t minus psi, isn't it? That is what we did. So, in this way you can see we obtained a particular part of the response to the actual force f naught cos omega t. So, let us go to next page. So, now we can write the total response, because the complementary part of the response already we have found in the previous part where we did the free vibration analysis. So, the total solution x of t, right. So, this is the total response or solution, and this is equal to xc plus xp, right. So, now let us assume the system to be underdamped, and then for the case of underdamped system we have obtained the complementary part as a e to the power minus zeta omega n t into cos omega d t minus phi, okay, this we got, and then we have the particular part which is x static upon under root of 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n whole square, right, into cos omega t minus psi, correct. So, that becomes basically the total response. Also note that here the a and phi, they are arbitrary constants. Here a and phi are arbitrary constants, and they can be obtained by applying initial conditions on the total response x. So, here we see that this part this part, the frequency of this part is, the frequency is omega d, isn't it, and it has a phase of phi, and then it is its amplitude it decays with time, correct. So, e to the power minus zeta omega n t, value of e to the power minus zeta omega n t reduces with time, and therefore, the amplitude of this part reduces with time, and that is why this part is called transient part, because it basically reduces with time and then disappears after some time. So, therefore, this is called transient part of the response. And now, if you look at this part, the second part, which is particular part, though the frequency of this part is omega, okay, while the frequency of the transient part was the damped natural frequency omega d, which is under root of 1 minus zeta square into omega n, right. So, that was a system property that depended on the system parameters, but the frequency of this particular part is omega, which is the frequency of excitation force which is acting, okay. And then the amplitude of this part is constant, okay. We can see the amplitude x static upon this term in the denominator, this is constant for a given omega. So, it means that this part will basically stay as long as the force is acting, okay. So, therefore, this part is going to stay. So, what happens as time progresses, the transient part would gradually decay and will become very negligible after initial time, and then only the particular part would be left, right. And therefore, in the steady state the total solution will be basically consisting of the particular part, and that is why the particular part is also called steady state part of the response. It is also called steady state response, because this is the part of the response that is going to be left under the steady state. Let us try to sketch the transient and steady state part in the total response. So, the transient part of the response is basically decaying in nature, right. So, it is going to basically decay like this, okay, and then we have the steady state part. The steady state part of the response is going to basically vary with frequency omega, and the amplitude of this part will remain constant like this, okay. So, this is x c as a function of time, this is x p as a function of time. Let us sketch total response here like this. So, here we are going to sketch x as a function of time. So, okay. So, what we see in the initial part there is presence of transient which is visible, but then after that the only the particular part is left, which is the steady state, okay. So, we see that the particular part of the response, so the steady state part of the response, it depends on two factors. One is what is the frequency of excitation omega, and what is the damping factor, okay. So, let us look at the steady state response. Right, it depends on the frequency of excitation omega and damping factor zeta, isn't it. So, if we try to show the variation of the steady state amplitude as a function of frequency for a given system with some damping factor zeta, then this will be essentially like this. So, here we are showing the amplitude xpo, right, and this would basically look something like this. Okay. So, this is basically the resonant frequency here, isn't it. So, we see that when omega is much less than omega n, then this response is basically equal to, amplitude of the response is equal to x static, right, and somewhere when the frequency is close to resonance and around resonance, the response is very high, and when omega is very large as compared to omega n, the response becomes negligible, right. So, it would be interesting to understand dynamic equilibrium of different forces in a viscously damped system. So, let us try to look at dynamic equilibrium of forces. Okay. So, let us now show on a complex plane the complex exponential forces. So, here we are assuming that the force is complex exponential of type f naught e to the power I omega t. So, the response x, the velocity x dot and acceleration x double dot, they also will be corresponding complex quantities, and these complex quantities then we can represent in the complex plane as rotating vectors. But the actual force and actual displacement, velocity and acceleration will be the real parts of these complex vectors. So, taking the real part on the real axis basically will tell us the actual values of the force, displacement, velocity and acceleration. Therefore, we have, let us say this is the force vector, this is f bar, right, and then we have the the displacement vector is like this here, this is x bar, right, and it has a phase lag of basically psi. Okay. So, displacement lags the force by phase angle psi. Then we have the velocity which basically leads the displacement by 90 degree, and then we have the acceleration vector which basically leads the velocity by 90 degree, like this. So, this is how the force and various kinematic quantities are related. Let us now try to sketch the forces. So, we make another vector diagram here like this, and here again we are going to now show the force first. This is the force, right, which is F bar, okay, and now we are going to show the force due to elasticity, right, and that force would be basically this. So, here also we are assuming that the omega is much less than omega n, okay. So, all these diagrams we are making for the case when omega is much less than omega n. So, this would be basically the elastic force, force due to stiffness. Then we have the inertia force which will be basically this, right, this will be m x bar double dot, and then we have the force due to damping which will be this opposite to the velocity which is c x bar dot, isn't it. So, these are how different forces are placed, and now we can make a vector polygon of these forces as they are in equilibrium. So, we have this force F bar, okay, then we have this force due to elasticity which is this, which is k x bar, okay, and then we have the force due to damping which is c x bar dot, and then we have the force due to inertia. M x bar double dot. So, what we see here that the one component of the force basically balances the damping force, and other component along with the inertia force balances the stiffness force. So, this is how the dynamic equilibrium basically is achieved. Now, let us see what is this equilibrium at when omega is equal to omega n. Omega is equal to omega n, right, when the resonance occurs, then what kind of equilibrium is there. So, let us make that diagram. So, here we have this the force, this is F bar, right, So, the velocity will be in phase with the force. So, the velocity vector is somewhere here x bar dot, right, and then the displacement vector would be somewhere here x bar, and then we have the acceleration vector which is x bar dot, correct. And if we now make the force diagram, then this is the force F bar, okay, and now the damping force would be opposite to the velocity. So, this is the damping force, this is x bar dot, right, and then we have the force due to elasticity which is k x bar, right, and then we have the force due to inertia, that is inertia force m x bar double dot, correct. And now if you make the vector polygon of these forces, then that polygon would be something like this, that you have this the force vector, and then you have the force due to elasticity which is k x bar, okay, then you have the force due to damping which is c x bar dot, and then you have the force due to inertia which is m x bar double dot, correct. So, we see that at omega to omega n, inertia force and stiffness force balances each other, and the damping force alone basically balances the external force, and that is why the response is very high at resonance, okay. So, only the damping force or the damping in the system basically controls the response at resonance, and because system is vibrating at natural frequency, it is expected that the spring force or the stiffness force will basically balance the inertia force, because that basically defines the equilibrium at the vibration at natural frequency, right. So, let us finally look at what is frequency response function FRF. So, earlier we defined FRF alpha omega, right, as ratio of the steady state part of the response, okay. So, in this case that response is x bar p o, right, divided by f naught, okay, and x bar p o we obtained as f naught upon k minus m omega square I omega c, okay, and f naught divided by f naught. So, therefore, what we get the expression 1 upon k minus m omega square I omega c, correct. So, this is the expression we get for the frequency response function, and if we divide it by say m in the numerator and denominator, we can also write this expression in this form omega n square minus omega square plus I 2 zeta omega omega n. So, we can also write this in this form, okay. So, you can see that the FRF is now complex, it has both magnitude and phase. So, in this way we come to the end of this lecture, and in this lecture we basically discuss the free and force vibration of single degree of freedom system with viscous damping. Now, we stop here. Thank you.